Welcome back, students. Today we will be deriving the equations of uniformly accelerated motion using the method of calculus. You have already learned how to derive the equations of motion using graphical method. You know what is the different set of equations that are utilized for understanding dynamics of motion. Now today we will be understanding a new method in order to derive the same batch of equations that are commonly known as the velocity time relation, which is V equal to U plus AT, position time relation, or that is also called the displacement time relation, given by S equal to UT plus a half AT square, position velocity relation, or sometimes also called the displacement velocity relation, that is V square equal to U square plus 2as, and lastly distance traveled in the nth second, that is given by Sn equal to U plus a by 2 2n minus 1. These are the four equations of motion that will be derived using the calculus method today. Now, when I'm talking about the calculus method, I mean we will be employing the methods of integration and differentiation. Very elementary expressions will be used, as I had already told you during the classes on integration and differentiation, that even though several expressions has been discussed, but still we will be sticking to only one expression while deriving all the equations in physics, so that you will find, and very easily, very conveniently, using this method of calculus, we will be deriving these four equations of motion. So let's begin with the first one, that is the velocity time relation. For this, I will begin with the expression for acceleration. Acceleration by definition is rate of change of velocity with respect to time. Now, whenever we talk about rate of change in calculus, we generally utilize an understanding of an infinitesimal small change in velocity with respect to a corresponding change in time. So, if the change in velocity is dv in a small duration of time dt, then acceleration will be given by dv by dt. Small change in velocity and small change of time, that is the first derivative. So A is equal to dv by dt. Let's write down the same expression in a slightly modified form. So we will get dv equal to A dt. dv equal to A dt. Now comes the important step. Integrating both sides. Now here again I will like to clarify what is integration. Integration is nothing but summation. Since we have considered very small changes in velocity for a very small change in time, so obviously a question might arise that what is going to be the total change in velocity over the total duration of time. So whenever we are talking about total, we usually do that the summation of these elementary parts needs to be done. Whatever elementary, whatever infinitesimally small values have been considered, if we add it up, if we add up all these values, then obviously we will get the total value. And integration is nothing but summation of these very small parts. So we need to integrate both the sides of these expression. So we have to symbolically write it down as integral dv equal to integral A dt. Before I proceed further, here again an important rule that you need to remember. Actually, you will be utilizing this rule in the next all the cases whenever you are carrying out differentiation or integration. Talking about a term which is referred to as a constant. A constant by definition is a quantity that does not change its value over time. So can you identify the constant quantity over here? Which is constant? V, A or T? Obviously A is constant. We are talking about uniform acceleration. Uniform acceleration is nothing but constant value of acceleration. So if acceleration is constant, so what is its role within the integral sign? Integration or differentiation is carried out for terms that are undergoing some change, that are variable. So a constant term has got nothing to do, absolutely nothing to do, that it should be retained within the integral sign. So in the next step itself, what shall we do? We shall remove the constant term and take it out of the integral sign. So now the integral turns out to be something like this. Now let us utilize the values of the terms at the beginning of the measurement and at the end of the measurement. That is, I am trying to figure out the limits, and instead of having an indefinite integral, we shall have a definite integral. I hope you remember what is a definite integral. Definite integral is an integration where the limits are known. This means the range over which integration is being carried out, that is known to us. So obviously the measurement is beginning at time equal to 0. The corresponding to time equal to 0, what is the velocity of the object? Obviously the initial velocity u. The measurement will begin at final time t. Corresponding to final time t, we can assume that the velocity of the object has become v. So now over these limits, we have to carry out the integration. We are having the general expression for integration, but the question arises, which standard integral does it represent? Can you identify which standard integral can be used to write down the result? Because straight away we can write down the result using the standard integral. For that, you need to remember this integral. Integral x to the power n dx is equal to x to the power n plus 1 by n plus 1. Now you might be wondering that the above expression, which term can be written as x to the power n? What is x? What is n? Now let me show you. For example, if n is equal to 0, if n is equal to 0, then how will this integral be written? We can write down integral x to the power 0 dx equal to x to the power, in place of n we can write down 0, so 0 plus 1 by 0 plus 1, and that will be equal to simply x, isn't it? X to the power 0 plus 1, that is x to the power 1 by 1, it is x. So now compare this expression with the above written integral. You are having dv on one side, you don't have any term having v. Similarly on the other side you are having dt, but you don't have any term having t. So now let us write down the above expression in a slightly modified form. You don't have any term having v, so we can write down v to the power 0, because anything raised to the power 0 is 1. So it is not going to make any difference. So I can write down v to the power 0 into dv. It is still going to remain as dv because anything raised to the power 0 is 1. And we can substitute the limits as u and v. Similarly on the other side you are having a. Instead of writing dt, we write down t to the power 0 into dt and put the limits as 0 and t. Now can you relate this integral with the standard integral? Of course, you can do it. So now we can use the result that I have written over here. Use this result and straight away write down the expressions. So on the left hand side you get v raised to the power 1 plus you will get v raised to the power 0 plus 1 by 0 plus 1, putting the limits u and v equal to a t to the power 0 plus 1 divided by 0 plus 1 and the limits 0 and t, isn't it? So now 0 plus 1 is equal to 1. So you can write down straight away v on the left hand side. In the numerator also you are having 0 plus 1, that is equal to 1, and that can be omitted. So now it becomes v with the limits u and v equal to a with the limits for t as 0 and t. You can write it down as v minus u equal to a t minus 0, and in the last step you can write down v minus u equal to a t or v equal to u plus a t. This is the first equation of motion, first equation of uniformly accelerated motion, or what is called the velocity time relation. So as you can see, using the method of calculus we have obtained the first equation of motion. Now just tell me, were the steps that difficult? Even though we have introduced a new method for calculating the same formula or deriving the same formula, yet the steps are so simple. And as I had promised you that we would be making use of the same expression, the same standard integral for deriving all the important equations, you will see that while deriving all the equations we are making use of the same standard integral. So it will be very convenient for you to remember, but obviously it will require a bit of practice. The steps are very simple and I hope it will be extremely easy for you to practice. So shall we proceed with the next equation of motion? Obviously. Now we have the position time relation. We know the position time relation is s equal to ut plus half at square. So let's begin deriving it. For this we will write down v equal to dx by dt. V is equal to dx by dt. As acceleration is equal to dv by dt, similarly v, that is the velocity of the object or the speed of the object, can be written as change in position with respect to time. Small change in position is represented by dx and small change in time is represented by dt. So the first derivative of x with respect to time, dx by dt, is the notation for v in calculus. So v can be written as dx by dt. Again, let us do a little bit of change. So we can write down dx equal to v dt. Can we? Obviously we can write down. Now from first equation of motion, we know that v is equal to u plus a t. Just now we have derived it. So can we express v in this equation as v equal to u plus a t? Obviously we can do it. So now we will write down dx equal to, instead of v I will write down u plus a t, and close it within brackets and then write down dt. Just check it out once again. Dx equal to v dt. So in place of dx I have written dx, in place of v I have written u plus a t, and in place of dt again it is simply dt. We have to remove the brackets, so we have to multiply. So obviously it becomes u dt plus a t dt. So you are having u dt plus a t dt. Now we can integrate. So now integrating both sides of the equation. Before we integrate, we have to also understand the initial values. What is the initial value of x? We can put the initial position of x as x0. For time it is 0. For final value of time it is obviously t. So let us put the integral sign and write down dx equal to u dt, put the integral sign, plus integral a t dt. This is how the integral is going to turn out. Now, if you remember, I had told you during the previous integration that whenever there is a constant term, the constant term does not change its value with time. So, obviously, it can be taken out of the integral sign. Check out both sides of the equation. Do you have any constant term on the left hand side? No. There is only one term, that is dx. Position is changing. On the right hand side, there are two terms, u dt, at dt. In the first term, you are having a constant term, that is initial velocity u. Initial velocity is a fixed value, the velocity which was present in the body at the beginning of the measurement. So, obviously, it is not going to change. Either the velocity will increase or decrease once time starts. So, at the beginning of measurement, when time is 0, the velocity of the object, that is u, is a constant quantity. So, that can be taken out. And as usual, this equation is for uniformly accelerated motion. So, again acceleration is constant, and that can be taken out of the integral sign. So, now we can write down dx with an integral sign equal to u integral dt plus a integral t dt. Let's substitute the values. So, time equal to 0, let the position of the object be x0. At time equal to t, let the object reach a position x. Using these values, let us carry out the integral. And again, I will like to remember that we are making use of the same standard integral. X to the power n dx is equal to x to the power n plus 1 by n plus 1. We would be using the same standard integral. So, don't be confused. This same integral will be used again and again. Let's go back to the point where we had left. So, now we will write down the results. See, dx, that can be written as integral isn't it? We can write it down. Now we will be writing down the result. This will become x put the limits x to u. This will become t, put the limits t plus a, and this will become t square by 2, put the limits 0 and t. How does it become t square by 2? I hope you remember t dt. This means t to the power 1, and it should become t to the power 1 plus 1 by 1 plus 1. So, t to the power 1 plus 1 means t square, and in the denominator 1 plus 1 means 2. So, t square by 2. Now, we need to substitute the limits. We will get x minus x0 equal to u t minus 0 plus a t square by 2 minus 0 square by 2. So, if we put x minus x0 equal to s, if this be the displacement, therefore we can write down s equal to u, t minus 0 is t, plus a t square by 2 minus 0 square by 2, that will give us t square by 2, and we are left out with the second equation of motion, that is s equal to ut plus at square by 2, or s equal to ut plus half at square. So again you can see that very easily, very simply, using the method of calculus, we can obtain the second equation of motion. Now before we proceed any further, just let me know if you are having any doubts in the first and the second equation of motion. Hopefully you shouldn't have any doubt, because the steps are very simple. And as I was reminding you, a little bit of practice is required on your part, because you are using a standard integral again and again, so you need to memorize the expression, because unless you remember what is going to be the result for the standard integral, you will not be able to substitute it accurately while doing the calculations. So now let's proceed with the next one. Velocity displacement relation, that is v square equal to u square plus 2as. We will be deriving this expression using the method of calculus. For this, we will again begin with the expression for acceleration, that is equal to dv by dt. Let us do a little bit of modification. We can write down a equal to dv by dx into dx by dt, isn't it? Can't we write it down as a equal to dv by dx into dx by dt? Obviously we can. Now what is dx by dt? I hope you remember, dx by dt is velocity. So now we can write down, therefore a equal to dv by dx into v, or we can write down a equal to v dv by dx. Let's cross it, so we will get v dv equal to a dx. At this point comes the important step. Integrating both sides, and obviously we have to take care of the limits. Integral v dv equal to, can I skip one step? You already know that acceleration is the constant term, so why can't I write it down outside only? Integral a dx. It's simple, because a is constant. Now what should be the limits? At the initial state, when the measurement begins, the object was as a position x0 and the velocity of the object was u. Finally, the object reaches a position x when the velocity becomes v. Keeping in mind these limits, let us carry out the integral. Now, at this point, if you have taken a note of this expression, I will do one more modification. Well, let me write it down again. I can write down this same expression as v dv equal to a integral x to the power 0 dx. This was the modification that I was talking about. So now let us straight away write down the result. So this will become v square by 2 with the limits u and v, and this will become a x with the limits x0 and x. So now in the next step we can write down v square by 2 minus u square by 2. How? Because first we put v in place of v, and next step you put u in place of v. So you get v square by 2 minus u square by 2. On the other side you get equal to a x minus x0. If Again similarly we can write down fx minus x0 is equal to s. So we can write down half v square minus u square equal to a into s. So now you can write down v square minus u square equal to 2as, or you get v square equal to u square plus 2as. So this is the third equation of uniformly accelerated motion that we have derived using the which method? Calculus method. So now I hope that you can understand how using the method of calculus very easily we can obtain all the three sets of equations. Now still we are left with one, that is distance traveled in the nth second. So let's proceed for deriving this expression, distance traveled in the nth second. For this I will begin with the expression v equal to dx by dt. V equal to dx by dt, and then I will write down dx equal to v dt. Okay, dx equal to v dt, as v is equal to u plus a t. Therefore we can write down dx equal to u plus a t into dt. You will find that we are still now following the same steps as we had followed while deriving the second equation of motion. So dx is equal to u plus at dt. Let's remove the bracket. We will get dx equal to u dt plus at dt. Check it out, u dt plus at dt. Okay, now integrating both sides. On one side you are having dx integral, that is equal to, I am keeping the constant terms outside, so you will get u integral dt plus a integral t dt. Now at this point comes the very important thing to be considered. What are the limits over which we have to carry out this integration, because that is going to decide the expression that we are going to obtain for distance traveled in the nth second. Here again I would like to clarify what is nth second. Nth second represents a moment. N may have any value 1, 2, 3, 4, 5 and so on, but it is that particular second. What is the distance traveled in the fifth second? Suppose n is equal to 5, then what is the distance traveled by the object in the fifth second? So how to calculate it out? For that we have to see what is the distance traveled by the object in total 5 seconds, and then what is the distance traveled by the object in the total 4 seconds. Taking out the difference between these two values, we can see what is the distance traveled in that 1 second, that fifth second. You can generalize it. Talking about distance traveled in n seconds, we have to find out the distance traveled by the object in total n seconds and then total n minus 1 seconds. Finding out the difference, we can get the expression. Suppose the distance traveled is to be calculated for nth second. So at time equal to n minus 1, if the distance traveled is s n minus 1, or rather we denote it with x only. So if suppose it is x n minus 1, then for time n the distance traveled is x n. So now we have to write down the expressions. So on one side you are having integral. Similarly you can write down x to the power 0 dx equal to u integral t to the power 0 dt plus a integral t dt, and then let's us put the limits. We will write down okay. Let's proceed with the integration. Using the standard integral, you get x, and then for the limits you are having x n minus 1 and x n. Mind it, this is in the subscript. Equal to u, you are having t, and then you are having n minus 1 and n, plus a, you are having t square by 2, and then for the limits we are having n minus 1 and n. Now we have to do a bit of calculation. So on the left hand side you get xn minus x n minus 1. On the other side you have u. Now we have to substitute. First in place of t, what I have to write? N. And next in place of t, I have to write n minus 1. Intentionally I have put a bracket because I have to take care of the sign also. Plus, use a separate line, a. See, I can take out this 2, so it will become a by 2. In the first case, in place of t, what I have to write? N. So it will become n square minus. In the next case, what I have to write in place of t? I have to write down n minus 1. So it will become n minus 1 square. So now I have to do this calculation, and hopefully you will understand why I have put this bracket, so that it becomes convenient for me to take care of the sign also, because that is very important. Let xn minus xn minus 1 be denoted by Sn. So now in the next step I will write down Sn equal to, let's do the calculation. It will become u n minus n plus 1. See, n minus n, minus minus plus, plus 1. So n minus n plus 1, n minus n plus 1, plus a by 2. In this case, first of all, let us do the expansion. So n square minus, in the second term you are having n minus 1 whole square. So it is in the form of which algebraic identity? It is in the form of a minus b whole square. So you can write down a square plus b square minus 2ab. So you can write down n square plus 1 minus 2n. Close the brackets. Now we will remove the bracket because we have written all the terms. So Sn will be equal to u. You can see you can cancel out n. You are left with 1. So it is 1 plus a by 2. In this case we are having n square minus n square, minus plus minus 1 minus minus plus 2n. So again you can cancel out these two terms. So you are left with 2n minus 1. So straight away you get Sn equal to u plus a by 2 2n minus 1, and that is the expression for distance travelled in the nth second. So now, using the method of calculus, you have seen how conveniently we can derive these 4 important equations of motion, based upon which you will be getting many numerical questions. And for practice of these numerical questions, you need to understand how this formula are derived. You may be getting derivation type questions as well as some numerical questions based upon these four expressions. So you should practice many questions based upon this formula. And obviously, as far as the method of derivation is concerned, you have studied two methods. First is the graphical method and second is the calculus method. So both are of equal importance and you have to study them properly. Thank you.